Good day to all. Welcome to this lecture on the Unit 3. So, in this video, we are going to see about the inductance and the magnetic energy density. As you all know, the inductor as a circuit element in your circuit theory course. So, as you will be knowing that inductor is going to be constructed by a particular ferromagnetic material as a core. So, if you are winding on particular conducting wire is going to be wounded on a particular ferromagnetic material, then that arrangement is going to be called as the inductor. As you know, this inductance is on property of a circuit element. If that particular arrangement is going to be a physical arrangement of whatever we have defined in the we have defined now, that is going to be inductance in nature. So the inductance or inductor are going to be the physical property of the circuit arrangement of a coil that is being wound on a ferromagnetic material or a magnetic path. So here we have mentioned that particular arrangement as we have say the particular coil is being wound around a air core. So this particular core can be an air core or it can be an ferromagnetic core, but here we are going to take only the air core. If you are assuming that particular core is going to be a ferromagnetic core, then the magnetic field calculations or the equations are going to be non-linear in nature. But we are going to only represent the linearity properties and the linearity relationships of magnetic field equations. So we have taken only the air core here. So for the air core only, we are going to define the inductance here. So in order to define the inductance, first we are going to see what do you mean by flux linkage. So the first primary concept of inductance is going to be developed from the definition of the flux linkage. So in order to know what is the flux linkage, first we know that flux, that is the magnetic flux, is going to be equal to the surface integration of beta ds vector. So this definition we know from the discussions of the magnetic flux density. So here since we are having this particular coil arrangement, this coil arrangement having n identical turns, since this particular n identical turns are going to be produce a magnetic flux density of B vector. So if that is going to be the case, then we can represent this particular flux as a surface integration of beta ds vector. Then we can define the flux linkage of this particular circuit as lambda is equal to n into psi, because we are having the n identical turns in this particular coil arrangement. So that is going to be the case. Then flux linkage lambda is equal to n into psi is going to be represented for the linear case. So if it is going to be, if the medium is going to be as a linear, that is we are having only the air core, not having ferromagnetic material, so our medium is going to be linear. So if it is going to be linear, then lambda is directly proportional to the I. This proportionality constant is going to be L. This L is going to be represented as an inductance, or it is going to be a constant of proportionality. Since we have defined the inductance as a property of physical arrangement of this circuit, then from the equation number 2 we can represent L as a lambda divided by I, that is the ratio between the flux linkage per current. So since we know the flux linkage is equal to n into psi, So we will be having L is equal to N into psi divided by I. Since we are representing this as an proportionality constant or a new term which is discussed here, the units of this particular inductance can be given as an Henry, or it can be Weber per ampere. Why we are having this particular Weber per ampere? So this Weber is going to be the unit for the magnetic flux or flux linkage. So magnetic flux divided by, or the magnetic flux linkage divided by current is going to be the inductance. So we are having Weber per ampere, that is going to be represented as a common unit of Henry. This particular inductance is going to be termed as a self-inductance. Since this self-inductance is going, normally the inductance is going to be amount of magnetic energy that is stored in the inductor. So the energy stored in the particular inductor or a magnetic field is going to be half into Li square. So from this equation also, if you are going to represent this particular inductance in terms of magnetic energy, then 2 into Wm divided by I square by rearranging this equation. Since we have only come across with the flux linkage of that particular magnetic circuit, that is by applying the current in a particular coil, then that particular magnetic field is going to link with that particular coil itself, then that particular produced inductance can be a self-inductance. But that is not the only case that is going to happen in the physical phenomena, but the mutual inductance is also going to take care, because the flux linkage of the particular coil is going to link only not only the same coil, but it can link other coils also. So if it is going to be the case, then we will be coming across with the mutual inductance also. So the mutual inductance can be represented by this diagram. So here we are having two coil arrangements. So the two coil arrangements are separated by an air medium. So since these two coils have been separated by an air medium, we will be having flux linkage between these two coils. Here we have represented flux linkages, some of these flux linkages here. I have represented this particular flux linkage in a bigger diagram in the bottom diagram. So here I am going to mention some of the flux linkage concepts here. You can see here we are having the current is going to flow by this direction, and in the second coil we are having the current is flowing by this direction. So I2, since we are this particular I1 and I2 are going to entered into the negative side of this particular battery, so we are representing the I1 and I2 as we have mentioned that it is going to enter into the negative side of the battery. So that is going to be a common representation of the current in any of the magnetic circuits. ஒரு நிமிஷம் அங்க இருக்காங்க, ஒரு நிமிஷம். ஆமா, so here we are having the mutual inductance of these two linkages. So we are having this particular linkage of two fluxes. So here we are having the current is going to flow by this particular direction. Due to the presence of the current in this particular direction, we are having the current is flowing into the coils in this directions. since we are having the current is flowing into these directions, as we know from the representation of magnetic field by the flow of current, and that particular flow of current is going to be represented by the right hand thumb rule. If you are going to represent that particular right hand thumb into the direction of the current, and other fingers are going to represent the magnetic flux direction, then this particular psi 11, that is going to be the flux linkage of the coil number 1 in the particular coil number 1 itself. So if it is going to be the case, then this particular linkage of the flux is going to be acting along the clockwise direction. Also, here you can take this particular direction also. So into the coil, the current direction is going to be from the left to right. So if this particular current direction is from left to right, then if you represent that particular current direction as a thumb finger, and other fingers are going to represent the direction of the flux, that is going to be a clockwise direction. So since these two fluxes are going to be in clockwise direction, the mutual fluxes are going to be in the same directions also, because we are having the clockwise rotation of the flux in the self-inductance also. But since these two are going to be represented in the same clockwise rotation of the magnetic flux, then the mutual fluxes are also going to be in the same direction. So since this is going to be the case, then we can represent the flux linkages as psi 11 as flux in the coil number 1 due to the current in the coil number 1, that is going to be a self-inductance. Then that is going to represent as an flux linkage for the self-inductance. For mutual inductance, we will be having the psi 1 2, that is the flux in the coil number 1 due to the current in the coil number 2, and we can represent psi 21 as a flux in the coil number 2 due to the current in the coil number 1, that is going to be a mutual inductance in nature. And the last one is going to be psi 22, that is going to be flux in the coil number 2 due to the current in the coil number 2, that is going to be a self-inductance in nature. So since we have discussed with that particular flux linkages, then we can represent the mutual flux linkages of psi 1 2 as an flux linkage of flux in the coil number 1. It is going to due to the current in the coil number 2. Then we can represent this flux linkage as an integration of integration of surface, that is the surface integration of S1 area, that is going to be B2 into ds. And the mutual inductance M12 is going to be represented by the lambda 12 divided by I2, because that is the mutual inductance between in the coil number 1 due to the current in the coil number 2. So that is going to be represented by the flux linkage in the coil number 1 due to the current in the coil number 2. So lambda 12 divided by I2 is equal to N1 psi 12 divided by I2. So this mutual inductance is also going to be represented by the Henry units. So M21, that is going to be the mutual inductance in the coil number 2 due to the current in the coil number 1, that is going to be represented by the lambda 21, that is the flux linkage in the coil number 2 divided due to the current in the coil number 1 divided by I1, that is the current in the coil number 1. So N2 into psi 21 divided by I1 is going to be the mutual inductance in the coil number 2 by the current in the coil number 1. So if the medium is going to be linear, that is in the options of the ferromagnetic material, this M12 is going to be equivalent to the M21. We can represent the whole inductance as the summation of the self inductance and the mutual inductance in the same coil. So in the first L1 is going to be the lambda 11 divided by I1, that is going to be your self inductance. So that is going to be N1 into Psi1 divided by I1. L2 is equal to lambda 22 divided by I1 is equal to N2 into Psi2 divided by I2. So the total flux linkage Psi1 is equal to Psi11 plus Psi12, because these two flux linkages are going to link with the first coil itself, but the first linkage is going to be due to the current in the first coil, but the second is going to be due to the current in the second coil. So as the same one, the total flux linkage on the coil number 2 is going to be Psi21 plus Psi22, that is going to be represented as the flux linkage in the coil number 2 due to the current in the coil number 1 and due to the current in the coil number 2. So the total energy is going to be W1 plus W2 plus W12, that is going to be half into L1 I1 square plus half into L2 I2 square plus or minus M12 I1 I2. So in this particular equation we are having plus or minus. So plus is going to strengthen this particular total energy, and minus is going to weaken the total energy. So in which cases the strengthening of the energy will be taken is going to be when the mutual inductance, mutual fluxes in the particular coupled coil is going to be add each other. If these two fluxes are going to be add each other, then the energy is going to strengthen. If the two fluxes are in the opposite directions, then that is, one is in the clockwise direction, another one is going to be in the anti-clockwise direction, means then those two fields are going to weaken each other, so that the total energy is going to decrease. So this is all about the inductance concept. Next we are going to see about the magnetic energy density. In order to define what is the energy density, we may be given a particular entity of a volume of a cube, which is going to be represented by the del x, del y, and the del z. So this del x and del y are going to represent the length and breadth of one particular cube, and del z going to be represent the height of the cube. So if this particular cube is being supplied with an surface current density of del I, that is going to be in the upper and the bottom side of the particular surfaces. In the upper surface we will be having the del I direction as like this, and in the lower surface we are having the del I direction as like this. So if you are supplying with an B vector, that is the magnetic flux density is going to be supplied from the left to right, then what is the energy stored in the magnetic field? B is going to be represented by the Wm, which is going to be half into Li square. So if you are considering a differential volume in the magnetic field, the whole region is covered with such a volumes. So if you are assuming this is one volume, but if you are having the whole material is going to be covered with the magnetic with the such volumes, then each volume is going to have an inductance of del I, which is going to be represented by the flux linkage, that is the change in the flux linkage per change in the current. So the change in the flux direction is del psi divided by del I, which is going to be represented by the flux linkage can be given as the integration of beta ds divided by del I. since this particular B into surface area, so the B can be represented by the mu into H. So mu into H into this particular surface area is going to be represented by the surface which is being faced by this particular B direction. So the surface which is going to be faced by the B vector is going to be represented by the two axes, that is x and the z axis. So we will be having the surface is going to be represented by the del x and the del z. So mu h into del x into del z divided by del I. So also we will be having the del I is equal to h into del y. How we are getting this particular equation is from Ampere's law. So since we know in integration of h the dl is equal to I vector as an Ampere's law. So here h into particular differential length. So the particular h vector is going to act along the y axis. So we will be having this del y as an differential length. So h into del y is equal to del into I. So if you substitute this particular value in this particular equation, then we will be if you want to substitute this del w1, that is going to be half into del I into del I square. So if you substitute these two values, then we will be getting half into mu into h square del x del y del z. So if you have this particular equation as half into mu h square into del v. So the magnetostatic energy density is going to be represented by the Wm, which is going to be the limit of del v tends to 0, which is equal to del Wm divided by del v. So if you apply this equation, in this equation, if you apply this particular value, then we will be getting half into mu h square. We can write this particular Wm as half into bh, because we are having b as a mu into h. So this particular equation can be written as half into bh. Also we can write this particular equation as Wm is equal to b square divided by 2 mu, because we know b is equal to h into mu. So we can represent this particular magnetic energy density as b square divided by 2 mu. Thank you.